Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Artificial Hypothalamus and Benders-Decomposition. The material of conference was organized by the Engineer Jesús Velásquez Bermúdez, Ph.D. In 1962 J.F. Benders published his theory oriented to optimization of large-scale problems. The fundamental idea is the partition of a problem into two sub-problems of reduced complexity based on the division of the variables like coordination variables and subordinate variables. The solution of the original problem is obtained by the coordinated solution of two complementary subproblems. The coordinator linked to the coordination variables, and the subproblem linked to subordinate variables. The subproblem provides information to the coordinator by the dual variables associated with its constraints. The coordinator takes the information from the primary level and incorporates it in the form of hyperplanes, Benders cuts, limiting the feasibility region for the optimal solution of the coordination variables. Benders cuts represent the cost of subordinate variables as a function of the coordination variables. The algorithm defined by Benders is convergent and solves the original problem through the solution of the coordinator problem, applies only to linear subproblems. Multi-Benders decomposition, MBD, is a new approach developed by Velasquez, 2020, to solve complex mathematical optimization problems associated to large enterprises that may be decomposed using simultaneous different point of views, or hierarchical levels, for example, business, regions, zones, functions, etc. MDB integrates the concepts of artificial brains, developed to by Velasquez, 2021, using the theories developed by Jeff Hawkins, presented in his book A Millions of Brains, with Benders Multilevel Theory. Artificial hypothalamus structure. We define augmented artificial intelligence, AAI, as the creation of artificial intelligence from the neuroscience of human intelligence, integrated with the mathematical laws of smart physical systems. From human brain to artificial brain. The human brain is too complex to understand its functioning and synthesize it based on a unique mathematical algorithm. Neuroscience studies allow us to understand that within this high complexity there are infinitely large structures and infinite parallel processes that complies with many rules of regularity, hierarchy and symmetry. Then, based on these observable results, artificial approximations, aimed at building artificial brains for organizations can be constructed. In this understanding, large-scale optimization methodologies play a very important role. Now we can explore where we are. And where are we going? Traditional AI has concentrated on developing mathematical models, which try to imitate the functioning of mental intelligence, based on the structure of functioning of the brain, to represent the mental models associated with the processes of intuition, perception, deduction, just like humans, without using formal mathematical models, using fundamentally data-driven models. This process has been successful in relation to advanced predictive analytics since machines are able to emulate and overcome, in many facets, the mental functioning of humans. For example, pattern identification is increasingly performed by robots with greater precision and greater speed. This success is magnified when AI is given the ability to chain sequential recognition of multiple general patterns to a specific individual pattern, for example, identifying a specific person. Augmented artificial intelligence will be the new era of artificial intelligence will be based on the study of the operation of the neocortex and the real-time communication between algorithms, or cognitive robots, to build networks of mathematical models, that allow organizations to act in a similar way to the human brain, making intensive use of distributed processing. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and Hippocampus. The neocortex contains millions of neurons that communicate with each other to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to an array. In optimization models, it is common to use a matrix that relates columns with variables and equations with rows. The normal thing is that these matrices are sparse, structurally similar to that of the human cortex. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. The hippocampus. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. Artificial hippocampus store, like in the humans, the experience, and the knowledge acquired over time. The central axis of this possibility lies in developing a standardized language between algorithms, that allows to build an artificial hypothalamus so that multiple algorithms, representing agents, interact autonomously in real time, taking advantage of the information stored in an artificial hippocampus. This could be called Mathematical Programming 4.0. Based on distributed parallel mathematics, and not on the traditional concepts of monolithic and sequential electronic calculus. Artificial hypothalamus structure. We define augmented artificial intelligence, AAI, as the creation of artificial intelligence from the neuroscience of human intelligence, integrated with the mathematical laws of smart physical systems. Depending on its complexity, the ways to divide a system may be non-numerable. The diagram shows a two-level structure. This diagram shows a three-level structure. When comparing the human cortical structures with cortical structures of animals, it has been found that the complexity, number of layers and columns, increases with the intelligence of the living being. This is consistent with the fact that, the greater the complexity in the structure of optimization algorithms, speed off the solution time, and produce greater the understanding of the problem being faced. In a multi-level mathematical model structure, the different levels can be characterized by the type of processing they perform. Large-scale methodologies generates three processing areas. Holistic, that coordinate all processes and solves the problem. Communicative, all intermediate layers responsible for adjusting the information that is transferred between the upper layers and lower layers. Sensitive, intensive in generating basic information that produces the data that is processed in the upper layers. In dynamic systems it should be related with time dimension. When simple problem division methodologies are applied, verticalized structures are obtained, that ignore the transfer of horizontal communication. More complex methodologies, such as cross-decomposition, generate cross-structures like the real structures of neocortex. The image presents the real neocortical structure, and the Jeff Hawkins artificial intelligence structure. Everything indicates that the structure, and joint functioning of the neocortex and hypothalamus, is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the two disciplines, artificial intelligence and mathematical programming. Everything seems to indicate that, the Galileo Galilei's famous phrase, "Mathematics is the language with which God has written the universe," must include the structure of the human brain. Artificial hypothalamus structure. For real-world organizations and systems. Traditionally, low mathematical complexity modeling is based a top-down approach. In this approach, the process of disaggregation of the whole is carried out by empirical rules of proportionality, of low representativeness. Parallel computing has opened the way for bottom-up modeling, in which the system is built from atoms, whose operation is scientifically integrated. The advantages of this approach are having more layers of modeling, the atom's representation is more detailed. Having more atoms, the cells of the last layer, the mathematical problem is smaller, then the amount of resources required to solve the problem are less. Top-down implies a monolithic vision, based on sequential synchronous mathematics. Bottom-up a parallel vision, based on parallel asynchronous mathematics, oriented to large-scale optimization methodologies. The solution of an optimization problem using large-scale methodologies is based on partitioning the problem into two sub-problems that must be solved in coordination. It can be said that there are two basic methodologies that bring together majority of applications: Benders partition theory, BT, and Lagrangian relaxation, LR. They can be considered complementary. In BT, the partition is performed according to the variable's type. It is a primal method that works on primal feasible zone. In LR, the partition is performed according to the constraints type. It is a dual method that works on dual feasible zone. BT is a primal algorithm, also known as outer linearization or decomposition by quantities, or resources. In BT, variables are called coupling, or control, variables, and the remaining variables are dependent, or coordinated variables. The hierarchical relationship implies that, at the higher level operates the problem of coordination on control variables, and at the lower level the slave problem on coordinated variables is solved. This problem is parameterized in function of control variables. In response, the primary level returns information to the coordinator, focused on the value of the dual variables of its constraints. In its basic form, BT is applicable when subproblems are linear. A primal algorithm technique, or primal feasible, ever meets feasibility conditions, and only satisfied the optimality conditions when converged to the optimal solution. This implies that if the mathematical process ends without reaching the optimal solution, the solution of the primal variables is usable, because they meet the feasibility conditions, but it will not be optimal, because no meets the conditions of optimality. In this case there is an optimality gap. LR is a dual algorithm, dual feasible, also called interlinearization, or price decomposition. In LR the constraints are divided into coupling, or complicated, and the remaining constraints are considered easy constraints. The structure of the problem is such that if coupling constraints are ignored, it is possible to conceive of the optimization process as a simpler one, which in many cases can be subject to a decomposition process in multiple problems of less complexity. Two hierarchically sub-problems are established. At the upper level acts as a coordinating problem responsible for determining the dual variables of the coupling constraints. At the lower level a primary problem is solved about coordinated variables whose objective function is parameterized based on dual variables under the control of the coordinator. In response, the primary level returns information focused on the value of the primal variables. Subproblems in LR are not limited to be linear. A dual algorithm technique, or dual feasible, ever meets optimality conditions, and only satisfied the feasible conditions when it converged to the optimal solution. This implies that if the mathematical process ends without reaching the optimal solution, the solution of the primal variables is not usable, because they do not meet the feasibility conditions. In this case there is a feasibility gap. The methodologies of large scale are not limited to being mathematical tricks to solve the problem, they have a full techno-economic interpretation that helps to understand the inner workings of the systems. For example, in the case of BT applied to a multi-business company, the information that each subproblem generates corresponds to parts de Cobb-Douglas production functions, defined based on convex hull represented by cutting planes. The large-scale optimization methodologies define an exchange of information between problems, based on the duality theory. If we associate each subproblem with a robot, it can be said that Benders created a language to communicate mathematically cognitive robots, algorithms, working cooperatively to achieve a common goal. This is the same goal of the human hypothalamus. In a more general way, when the problem is divided into two levels, and the second level is broken down into multiple subproblems, a conversation can be visualized between a coordinator robot and several subordinated robots, who answer the questions asked by the coordinator. Artificial neural networks can also be associated to networks of algorithms, representing agents, of an organization, or system. Each of these agents could be associated with a superneuron that performs a much more complex transformation than that of a conventional neuron. On the other hand, the structure and communications of the artificial superneuron's net, ASN, are determined exactly by mathematics. In addition to the network, communications between neurons, centralized communications between mathematical problems or algorithms. Based on these concepts, Hy has developed the artificial brain framework, composed of a neocortex, a hypothalamus, and a hippocampus. Like the human hypothalamus, the artificial one is responsible for guaranteeing the balanced development of a company, coordinating in real time, algorithms that act autonomously and process information in a distributed way. An artificial hypothalamus can be seen as the intelligent and autonomous coordination of algorithms, or as coordination of robots. The concept of artificial hypothalamus can be applied to solve real-life problems from multiple points of view. In the diagram, the artificial hypothalamus coordinates models corresponding to the multiple problems faced by a company, organized from the point of view of its administrative functions. Another point of view is the spatial distribution of the problem. In this case, an artificial hypothalamus is presented for an agro-industrial company that has multiple facilities, farms, concentrated food factory, meat products factory, and stores in the food market. The artificial hypothalamus may be seen as a net of artificial superneurons nets. Asynchronous parallel optimization for artificial enterprise hypothalamus is viable thanks to supercomputers and superalgorithms that allow, at reasonable costs, to solve increasingly complex problems in increasingly shorter solution times. Hierarchies can be associated with multiple views of the same system, as Jeff Hawkins proposes. All models of the same system must work cooperatively. Considering the vision of large-scale optimization as multiple points of view, Hy developed the Benders Multi-Decomposition methodology. Partitioning and the decomposition of a system can occur in multiple ways, without there being a mathematical reason to select one as the best. The diagram presents a system that can be sorted hierarchically by three alternative criteria: business, regions, and functions. Alternatively, it is possible to choose another hierarchy: regions, business, and functions. It is important to note that in both cases it is met. The last layer, the sensory one, is the same since it corresponds to the atoms of the system. These could not change according to the point of view. The upper layer, the coordinators, is partially the same, since in each of them, the information corresponding to the alternative point of view is missing. To solve complex mathematical optimization problems associated to large enterprises, the optimization problem may be decomposed using different point of views. In many cases there is no obvious hierarchical order: first business after regions and finally functions? Or first regions then business and finally functions? Or the algebraic formulation depends on the hierarchical order, but the optimal solution must be the same regardless of the point of view. The advantage multi-decomposition arises when subproblems are solved based on an asynchronous parallel approach. In this case, each time a problem is solved, a cutting plane is included in the coordinator problem, in such a way that the number of mathematical elements included depends on the optimization process, the number of cores used, the numbers of vision of the system, and the structure of each of the subproblems. Then, it is possible to modify the standard large-scale methodologies to include mathematical elements from the different points of view, and they could speed off the solution process, and to have a better vision of the system. Each vision forms a processor within the hypothalamus, in this case organized by the regions. In this case, organized by business and by functions. This is the basis of the functioning of human hypothalamus, in which multiple networks of neural networks work in parallel, integrating the knowledge and giving the human being the ability to react appropriately, according to the speed at which it integrates information from different sources of knowledge. To the extent that a more complex structure is elaborated, the artificial hypothalamus becomes a supernet of artificial superneural nets. In simple multilevel Bender theory, in many cases there is no obvious hierarchical order for partitioning. MBD is a new approach that takes advantage of formulating multiple equivalent problems, one for each point of view, and formulating an extended coordinator model that integrates all points of view. The original problem, according to the structure suggested by Benders, can be considered for a single point of view PW. This problem may be called MDBPW. However, there are as many Benders formulations as there are points of view, as Jeff Hawkins says, multiple models of a unique object. Then, MDB problem can be associated with a problem with an angular matrix structure, which can be decomposed based on the points of view associated with the PW index. dx represents the value of the part of the objective function corresponding to x. To synchronize problems requires a coordination constraint, which indicates that the objective function for all points of view is equal to dx. With this restriction, the integrated formulation is ready to apply Benders decomposition. The value of dx is defined in the coordinator. This methodologically valid approach is rigid in the sense that it forces the models of all points of view to work with the same value of the objective function. The rigid is almost always worse than the flexible. For this reason, it is considered an alternative and equivalent modeling. To present the MBD theory, we consider a global energy company, which operates three businesses: electricity, transport of oil products, and oil production and refining. The company operates in three business regions: EMEA, America and Asia Pacific. And it considers that the three main administrative functions are production, global trading and treasury. The problem MDBB, oriented to the decomposition the firm according to business, is shows in the image. For the business point of view, the index PW equal to B. To differentiate the variables according to the point of view, the variables of the subproblem are VB. In the same way, matrices are differentiated for each subproblem. The matrices of all subproblems have the same elements, but ordered differently, depending on the point of view. The problem MDB are oriented to the decomposition the firm according the regions in which it operates, is shows in the image. For the region's point of view, the index PW equal to R. The problem MDBF oriented to the decomposition the firm according the main administrative functions is shows in the image. For the function's point of view, the index PW equal to F. Now, we have several different, but equivalent, problems, each according to a point of view. Since all formulations refer to the same problem, it must be met that in the optimal values of the objective function, theta b, theta r, and theta f, must be equal to the value of the problem solution, theta, and the variables for each problem, VB, WR, ZF, correspond to a matrixial transformation, alpha b, alpha r, and alpha f, of the original variable vector x. Considering the master problem of each point of view problem. If all three problems are solved independently, any of them will give the optimal solution, and the set of cutting planes would be equivalent in all cases. Then, exist an individual coordinator problem for each point of view. The sets ITIB, ITER, and IT differentiate the number of cuts generated by each subproblem for each decomposition dimension. The variables pi b, pi r, and pi f correspond to the dual variables of each subproblem. The variables theta b, theta r, and theta f define the objective functions of each coordinating problem, which is built based on decoupled cuts. Therefore, a solution is to solve all the problems in concurrent parallel, and the first one that achieves the optimal solution determines the end of the process. This approach is used in the main solvers, when there are different algorithms to solve a problem. The table summarizes the algebraic formulation of the individual subproblems. This formulation only considers cuts by optimality. Including feasibility cuts is a systematic process. The table summarizes the algebraic formulation of the individual subproblems. This formulation only considers cuts by optimality. Including feasibility cuts is a systematic process. An extended coordinator, integrating all points of view, can be formulated, following these principles. The cutting planes of all independent coordinators must be included in the unified coordinator. In a minimization problem, associated with each set of cutting planes, the variable q that determines the maximum value of the cutting planes must be defined. In this case, these variable qb, qr and qf. To build the coordinator, the variable phi is required, which comes from a cutting plane for the cost estimators of each point of view. The cutting plane set over the objective functions, theta b, theta r, and theta f, replaces the equality equations that must be satisfied by the optimal solution. During the optimization process, the difference of the values of theta b, theta r, and theta f allows flexibility in the movement of each subproblem, which should speed up the process. On the other hand, the highest value among these values will be an indicator of which is the critical point of view, which indicates to the coordinator how to select values of the y variables that pressure to increase costs in the most relaxed subproblems, that is, the subproblems that aspire to obtain a lower cost solution. The MBD coordination is closer to the coordination that is carried out in many companies, where central planning must meet multiple planning dimensions that must be attended simultaneously, as presented in the diagram. From a parallel computing point of view, each subproblem can be associated with a core or CPU setting that simultaneously generate asynchronous information to solve a common problem among all. This is the basis of the functioning of human hypothalamus, in which multiple networks of neural networks work in parallel, integrating the knowledge and giving the human being the ability to react appropriately, according to the speed at which it integrates information from different sources of knowledge. Benders-Decomposition theory and Industry 4.0. Under the principles of Industry 4.0, this corresponds to solve real-life problems under the real-time distributed optimization scheme, in which multiple agents take real-world information, big data coming from Internet of Things, to intelligently adapt to the permanent changes that occur in the real world. Multi-Benders decomposition using a unified coordinator can be implemented, using asynchronous parallel optimization. In the simplest case, one processor must be assigned to the unified coordinator, and multiple processors to the subproblems, ideally one per subproblem. In the case of the example, it would be 10 processors in total. The image shows a representation of an artificial hypothalamus using multi-Benders decomposition. Unlike the human being, where the hypothalamus, and all the functions required to survive and evolve, are created by life, in the business organization the humans, directives and executives, are responsible for creating the hypothalamus devices, vice presidencies, departments, of productive and administrative functions. In the industrial environment, the hypothalamus of the enterprise must be based on the knowledge of the process of serving the final products of its end customers, from the supply of raw materials and inputs that are required for this transformation. The construction of the hypothalamus, such as the construction of any service, must be the result of a design process, and its subsequent implementation, that is supported in a coherent methodology whose purpose is to produce the hypothalamus, according to the needs of the organization. For those who want to know more about the new artificial intelligence, are invited to watch the video, Artificial Brains, Augmented Artificial Intelligence. The new way of mathematics is directly related to the parallel thinking, and today it can be said that, like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Albert Einstein thought that imagination is the highest form of research. Thank you for your attention.